Let's just give them a big round of applause as they come up to the stage and share their amazing AI knowledge with us. Thank you guys so much.
Thanks, Randy. Thanks for the warm welcome. I'm Craig Dillman.
And I'm Karen Rhodes.
And does anyone want to take a crack at pronouncing the title of our message here different than Randy? No, I'm not trying to throw you under the bus, Randy, but the way you should know this from your movie trivia. There you go. You got to do it like Doc Brown. It's 1.21 gigawatts. So of course, you can tell already that I'm maybe a 1980s movie fan, and it seemed appropriate as we were doing some reading about power efficiency and AI workloads. You'll see the connection here in a minute, but we're talking about a lot of electricity. So I do a lot of work around AI workloads at HPE. I work closely with our NVIDIA partnership as well, who is very crucial to a lot of AI conversations. And we'll touch on a few things that we do together with them as we go through our presentation, but I'm honored to be on stage here with Karen Rhodes, and I'll let you introduce yourself.
Yeah, absolutely. So I'm one of HPE's distinguished technologists. I live here in Bella Vista, Arkansas, and have for the last 10 years. So I'm one of y'all. Feel free to come and ask me questions. Feel free to email me later on and get information. The better educated this community is, the better off we all are.
Okay. So Randy actually did pronounce it, I think, correctly. I say GIFs as well, not GIFs. So it's a gigawatt. But Doc Brown, we'll give Doc Brown the benefit of the doubt when he pronounced it a gigawatt back in the 1985 classic of Back to the Future. And if you remember that, he needed to generate 1.21 gigawatts of energy to, make his DeLorean travel through time. An interesting little piece of news popped up in September, just last month, that Microsoft is hiring, had posted a rec, I don't know if anyone saw this, posted a rec for a principal program manager for nuclear facilities because they are building small modular nuclear reactors to power the data centers where they house their cloud and their AI applications and solutions, which is open AI. And so Doc Brown was ahead of his time, right? If you remember the finer details, he needed a nuclear reaction to create the necessary 1.21 gigawatts. And so he just didn't know it yet, but we're in the same boat here today of needing nuclear power in order to generate what we need to facilitate these AI workloads. They demand a lot more power. In fact, GPT-3, so ChatGPT is pervasive in anyone's AI conversation these days because they have really brought to the forefront the accessibility of some of these AI workloads. GPT-3 was trained at a cost of 1.29 gigawatt hours. So very, very similar to what Doc Brown was looking for to make his DeLorean go. ChatGPT, or the GPT model, is requiring the same amount of thing. Now that's enough to power 120 average American households for a year. So what it took to train that model, that large language model, enough for 120 houses for a year is pretty crazy to think about. If you guys were in here earlier, did you see Zach and Vicente's creative AI session? Anyone in here for that? There you go. We got a live mid-journey image generation during the session. It was pretty slick. I tried to find out how much does it cost to what we just watched in that session. How much electricity did that cost? I couldn't find an answer for how much mid-journey would cost, but if you go back a few years from GPT-3, 3 or 4 years earlier, the first GPT model was trained, and the electricity cost was equivalent to about what it would take to the lifetime carbon footprint for 5 vehicles. So for however long they stay on the road, that model, that was in 2019. It was only 200 million parameters. What we're doing now, what the industry is doing now, is trillions of parameters. And so you can see it's not a surprise to any of us that there's this huge hockey stick effect of power demands for these AI workloads. The models themselves are getting larger and larger and larger and require much more computational power in order to train them and even run inference on them in time. But there's also a lot more of them. And so this was, I think, another kind of great impact of Zach and Vicente's session, take a look at the graph on the right here in front of you, where you may not be able to read all of the words there, but we're looking at global energy forecast for electricity. And by like 2030 is where you see the far right-hand side of that graph. The green section of that is data center power costs, data center power utilization. And so all of them are growing. AI is driving a lot of this, and will take much more of the overall data center power consumption. But another one to take note of, and we'll kind of come back to this when Karen's talking here in a minute, is the blue section of that graph. That's the network component of networks, wireless and wired networks, energy cost as you go. So those are also spiking tremendously. And one thing to keep in mind as you look at some of those is they're not heavily utilized. They're not using all of the power efficiently when they're deployed at the edge. So we'll consider that as we move forward. Now, anyone know what these are pictures of? I work for HPE, and we do a lot of things really well, and one of them that we do really, really well is supercomputing. These are all kind of some top HPC supercompute clusters. These are the things that like take up a whole room. The one at the bottom in the middle is called Frontier. It's just down the road from me. I'm near Nashville, and it's just down the road from me at Oak Ridge National Labs. These are massive supercomputers. You saw the jetpack guys, right? The Gravity Industries. They do jetpacks, like, which was pretty cool. At HPE, we do supercomputers. Nobody does supercomputers better than we do. At the bottom left is a picture of Seymour Cray all the way back in 1972. We've been doing supercomputers for decades. And when you start building these kind of high-scale, high-performance computing clusters, energy is very, very intentional part of the design criteria. And being able to get it right and get it efficient is kind of critical. It's a lot of very specialized subject matter experts that are kind of hyper specialized in being able to tune a system for efficient use. Okay, so let's stay on our 1980, actually still in 1985, so very specific movie references. 1985, go back in time and set the stage. And what I want to say, and Karen and I were talking about this earlier, is when you go to a supercomputing conference.
Go to Supercompute, by the way.
Yeah, Supercompute is coming up
Awesome.
in Denver in just a few weeks. Go to Supercompute. When you go there, you'll often go around the room and meet people, and it's kind of like, doctor, 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 doctor. And I think my friend Brad Shepard in the front here might have a prize for you if you can think of the Chevy Chase movie with the doctor scene. Oh, Spies Like Us. Right on, okay, so a John Hughes fan
Somebody
in the
got it.
audience, thank you. We'll see if we can find something fun for you. Come see us after. So, not only have we been building supercomputers for a while, we've been improving the efficiency. So the graph on the left, a lot of dots that you probably can't see, but what you should be able to see is that upward right trend. The y-axis is gigaflops, floating operations per second, gigaflops per watt. It's a measure of compute efficiency. How efficient can I get on the watt? And then the x-axis is a list of like the top 20, the top 15 entries into the Green 500. It's an HPC community, a supercomputing community group that measures efficient supercompute performance. The one on the far right is the one I showed you on the last slide. It's Frontier. It's the one at Oak Ridge. And way up in the top right corner, way more efficient than the rest of us or than the rest of the entries, is Frontier at like 65 gigaflops per watt. Now, you don't need to know what a gigaflop per watt is. That's okay, but it's very efficient. And so when we think about the AI workloads, training large models, the kind of infrastructure, the kind of design work that goes into it becomes very important. HPE has been doing that work at the cluster level, at the system level for a long time, but also at the data center level. So you get outside of the compute itself and start to see how do I make my data center operate efficiently. I want to tell you a little bit about the picture on the right because it's one of our newest facilities that we've moved into that our our data center design team, who has decades of experience here as well, has helped some of the principles that drive it. It's up in Canada, very cold climate, and so a lot of the cooling capacity is free for like 80% of the year. Average temperature in Quebec City, where this is like 30 degrees Fahrenheit. And so we can cool very efficiently a large space. It's very hydro, it's almost like 99% clean and renewable energy driven, hydro energy there. And one of the cool things that we're doing there too is heat, waste, capture, and reuse. And so they pump the excess heat or the offloaded heat from cooling our computers to a nearby greenhouse where in the middle of this 30-degree temperature, they're growing tomatoes. So there's some kind of cool applications of what we do there. Karen, let me turn it over to you to talk a little bit about what some other strategies beyond infrastructure and data centers could be to help mitigate these.
Absolutely. So on that previous slide, there's actually one thing. On that left-hand graph, if we were not around, you wouldn't actually see the top 2/3 of that chart, because the energy efficiency for HPE is the top 2/3. We are the most energy efficient on that. And that waterfall is actually a picture of the waterfall that runs that data center. So that is actually the waterfall feeding it. So it's pretty cool.
Yeah.
So when we went through the Industrial Revolution, think back in time, right? We had manufacturing plants where you had a steam engine very efficiently running, and it was powering machinery, right? Then we all got electricity. We democratized electricity. Every human being was able to plug in an appliance, and we see a line at the bottom. That is 1950, right? Everybody started getting home appliances, and then you see the level of power go through the roof. Now, we had some amazing advantages that happened with this as well, right? We had the assembly line. We had air conditioning. Air conditioning was the invention of the last decade, because you couldn't do a lot of the things that we do today without air conditioning, including supercomputing. But that democratization of electricity spiked the power. What we want to make sure that people are understanding is that we are now democratizing AI, and we're about to see another spike in the use of electricity, and we're trying to avert the inefficiency curve that's about to happen. So traditionally, AI, all of the things that we talk about up here, right? AI, large language models, all this fun stuff, these are just new workloads on supercomputers. We did protein folding, we've done deep space exploration. Those were all just use cases for these supercomputers. AI and LLMs, these are just the newest use cases for these systems, okay? They're just new apps that run on really big, powerful systems. Traditionally, you had people like NASA engineers that they are hyper competitive on getting the gigaflops per watt. Whenever I put it into my hand and I'm not able to see how much power that video or that picture rendering from AI is taking, how am I going to be responsible with the AI usage from a power perspective if I have no clue if that was as much carbon emissions as going to the corner store? Is there as much carbon emissions as going around the world in an airplane? I don't know as an end user, right? So as administrators, as creators of this technology, we have to be aware of this. There's another pretty scary chart at the bottom right. That's the global energy production, okay? And there's different models that show when we're going to run out of energy as far as being able to power these computers. But as you see AI adoption, you actually see a hockey stick that happens that is not on these normalized charts of the past. So we're actually going to be hitting that number faster, depending on which model. So we have to do something about this, okay? Everybody understands the problem, right? Yes. Okay, that's awesome. So we understand the problem. Now let's talk about how do we solve it? How do we actually affect change? In this community, I love living here. I love being part of this community because we can affect change at a global scale, each one of us, because of where we live, which is a wonderful thing. So let's talk about large language models and how you make those efficient. First thing is, you do not need to have a data set, a foundational model that goes back to the beginning of time. You do not need to have a large language model that knows Elvis Presley's birthday, right? That's not relevant to your business. You need a much smaller subset of your information. It's called a foundational model, okay? And then on top of that foundational model, you put your corporate information on top of it. Very small, okay? So first off, don't train on the world, just train on what's relevant to you, okay? Those foundational models are free, they're online, download them, they're lovely. When it comes to training the model, so that's the first piece is don't train on the world, you're gonna save a lot of power that way. The second one, any of you guys have kids? How many people have kids in the audience? Yeah, lots. Anybody tried to study anything whenever the kids were running around and they're asking for food? And yeah, how well did that work? Not great, right? Yeah, not great. So same thing happens whenever you're training a large language model. If you allow it to focus on just training, it's incredibly efficient. If you let it have all of the system's ability to just do that learning, it will do immensely more powerful than if it is distracted by jobs coming in and tasks swapping in and out, okay? Example, we had a customer 2 weeks ago that they had a large language model that was running in GCP. It took 2 weeks to train. They thought that was normal because these are new workloads. People don't know how long it takes. Brought it back on-prem. It still took 2 weeks because it was programmed to allow all of those different breaks in its communication. We did a couple of tweaks, told it this is how much hardware you have, use all of it. By using all of it, it changed 2 weeks of training, which is 336 hours, down to 2 hours. Same hardware, that's the difference in doing your tuning to make sure that it's actually using all of the system properly, okay? So when we're talking about power optimization, 336 hours of doing one function versus 2 hours, you have to train it before it can actually do the product for your business. I'd rather do that in 2 hours and take 2 hours of electricity. Make sense? Yep, okay. Now when it comes to using large language models, if I ask you to remember every time you've ever ridden a bicycle, how many people can remember that? Nobody. I can't remember that. If you ask a large language model for a question and you don't have any parameters around that prompt, you are asking on the full body of knowledge. However, if I ask you, when was the last time that you rode a bike? Can you remember the last time you rode a bike? Anybody? Yeah, that's easy to remember, right? It has context. Much easier to search on that finite set of data. That's what you need to do whenever you're using a large language model. So we'll take this as an example. You need to be putting an API on the front of your LLMs, maybe multiple API layers. It needs to ask who, what, when, where, and then the why actually goes back up. So who, what, when, where is downward facing. So if I am in this example, my prompt is, how do you weigh a bagel? If the person asking this is a baker, they are asking it about a bagel, they're at 5 a.m., they're at home, right? We have the ability to do this, to look at your phone and say, okay, this is who you are, this is your job function, this is where you are right now. You type in the prompt on your phone, that feeds into the API. Lovely. So I've got that information. The why that comes out is either they're getting education or they may have an idea. That why needs to go back into the business so that the business sees, number one, that the person is doing training. Number two, they may have an innovative idea that you need to tell that person how they can bring innovation into the business. They may not know that there's an innovation team in your organization. But by asking that finite set of questions, who, what, when, where, why, it's not asking the entire body of knowledge, it's asking a subset. So you will be able to run 1,000 queries instead of one query for the same amount of electricity, just by putting that API at the front end. Does that make sense? Okay, so I changed the person to a cashier. If they are asking, how do I weigh a bagel? Same parameters, they're at home, it's 5 a.m., probably woke up early with this noodling in their brain. They could be wanting education, but they also could be confused. If I have one person asking, how do I weigh a bagel, and they're a cashier, not a big deal. If I have 1,000 people that are cashiers asking, how do I weigh a bagel, I have fundamentally failed at educating my people that bagels should not be weighed. You should look at the number or it should be a bag, right? You're not supposed to weigh the bagel to charge somebody, right? I need to do an education and I'm not meeting the needs of my associates if they are asking that question. Does that make sense? So it's a feedback loop. This is the human in the loop. You need to always have the human in the loop to gain the efficiencies. So first, make your model small. Second, focus your model, make sure that it is absolutely dedicated, knows what gear it can actually run on, and the third, put that API in front of it, okay? Those are really easy things that you can do really today and get a massive jump start on your power. Now there's another thing. When we look at different AI systems, it's not just large language models, it's all kinds of things. There is a lot of inefficiencies, like Craig brought up, that it's not just the compute, it's also the network that's out there. And in supercomputing, there's something called a task scheduler. A task scheduler does exactly what it sounds like. It schedules tasks and tells it where they need to run at. Right now, most systems at the edge, whether it's in a truck, whether it's in a store, whether it's in a manufacturing plant, run at about 5% utilization. That is 95% of capacity that you're paying the electricity for, but you're not actually using. If you do a task scheduler, I can send a task out to that truck, and I can have it look at the vibration of the road and say, okay, vibration is high, but you're in Oklahoma. You know what? That's normal. Vibration's high and you're in Arkansas? No, that's not normal. Maybe we need to go ahead and get that truck into servicing, right? Who, what, when, where. Those are all important things. You have to have context around it, okay? By doing that, I am allowing that query to run on the truck or in the store. The velocity of gummy bears is something that I talk to a lot of retailers about, and it's somebody walks in and they sweep the shelf of gummy bears, they check out with all the gummy bears. That is a velocity that is abnormal. That needs to be alerting the merchant that there is a velocity of gummy bears that's too high in these 3 stores. Is that about to be a trend that's going across the country? It may be. But if they get that instantaneous real-time insight into what the buyer is doing, much better. I didn't actually send any data through the network. I saved all of that power. I didn't wait for the data to come back to the data center to do the query. That all ran in the store or on the truck or in the manufacturing plant, right? By running those small workloads where the data is created, we've created a better utilization of an underused asset out at the edge, in the truck, in the store, wherever. I've off-burdened the cloud, I've off-burdened the data center, so I can run bigger workloads in those consolidated locations, and I've unburdened the network by not making your data go from the edge back to a central location to make that decision. So these are just a few things that you can do right now, just easy steps on getting more power utilization out of what you already have. But this is something that we do all day long. So everybody's environment is a little bit different. Is it worth the squeeze to put something out at the edge? It may be, it may not be, right? Bring NVIDIA, bring HPE in. We are absolutely going to help you through this process. So with that, the power is now in your hands. So please use it responsibly. And we have 8 minutes left if anybody has questions. Nobody wants a gigaflop per watt question. Those are pretty crazy. So supercompute does happen in 3 weeks in Denver, right?
Yep, in Denver.
And you can attend virtually if you want to. So if you have folks that want to, just let us know. Yes, ma'am. Yeah. Can I do that one?
Yeah.
Awesome. Thank you. How does quantum computing change the power utilization for computing? Quantum computing does not make sense terrestrially. Quantum computing only makes sense extraterrestrially, in outer space. You need to be near 0 Kelvin, and outer space is just under 3 degrees Kelvin. So one of the pictures that you saw was actually Spaceborne 2. That was the second supercomputer that we've had on the International Space Station. So the first generation we had out there for, 5 years? And then this one we've had out for, I think, 3.
That's about right.
Yeah, we're learning amazing things about quantum particles and how they literally drill holes through memory and hard drives, and it makes us do better things on Earth. Quantum is a lovely thing. What is probably going to be the next step, though, before quantum, because that is better extraterrestrial than, because the power needed to cool it is just absolutely insane on Earth. The thing that is going to be the next step is going to be photonics. So we have an entire photonics on chip, so that is lasers that are on the chip. So instead of going into a transfer from me to you over a copper cable. We are literally shooting a laser between this chip and that chip. And the computers of tomorrow will basically look like a big light box with lots of lights going everywhere, and it's not too far away. We have several that are in our labs that have been running very well.